All right, hello everyone. How's it going? So this is part 3 of the series, and we're going to go into some of these more complex object detection models. Today we're going to cover faster RCNN. So I'm here at the README of the GitHub project, PyTorch Tutorials GitHub project. So if you scroll down to the Intro to Computer Vision section, and you're going to want to open up this in a new tab, and again save a copy to the drive so that you can actually edit it, follow along as you go. I think you're definitely going to get the most out of it by doing that. So okay, so I already have it open here. Let's get into it. Okay, so we're gonna sort of follow the same format that we have in the past 2 videos. But we're gonna be using faster RCNN on this toy data set and training faster RCNN to detect our circles, lines, and rectangle classes, right? Okay, so yeah, so we're going to use torchvision implementation of faster RCNN. We're not going to build this from scratch. This video is going to be long enough, people. So it's yeah, we're just going to use the torchvision implementation, but we're going to see how we can change the prediction layers at the end to change the number of output classes, so you can train on a custom number of output classes. And yeah, we're going to use PyTorch, torchvision, torch-lightning, and torchmetrics, just like we have in all the previous videos. Okay, yeah, so we'll start with our imports, build out this data set, and then compartmentalize that into the Lightning data module. And as a reminder for people, that data module is this nice sort of abstraction that pytorch-lightning has, where you can group your training, validation, and test sets all into one object, and then you feed that to your trainer, and it takes care of, well, you have to set it up, but it's very repeatable and reusable, and makes it much easier to share your deep learning projects with your collaborators or whoever is interested. Right, okay, so then we're going to visualize data. Then we're going to investigate this model. We're not going to build it from scratch, but we'll look at it and see how it works. Then we're going to overfit a small batch, build out our lightning module. So that's what's responsible for like doing the actual fit, right? Or, you know, doing the training. So it's going to contain the optimizer, it's going to contain the loss function, it's going to have the model, and it's also going to track our hyperparameters and track our metrics over the training, right? So hopefully all of that is familiar to people from the previous videos, because I'm going to try to make this one a little longer. I said that last time, and it was marginally longer, I mean shorter, but I'll try my best here. Okay, then we'll train, visualize the predictions, and wrap up. Okay, so first off, I want to introduce faster RCNN a little bit for people if this is new to you. I have, again, some links here, the general links that I show in every notebook, and then the faster RCNN specific resources. The first one is the paper and the original faster RCNN paper, and I've got that here. Let's see. So faster RCNN towards real-time object detection with region proposal networks. So they have this whole concept of a region proposal network, where basically they're able to just sort of like propose where they think objects could be, and very much reduce like the number of different possibilities of where objects could be in the image, and that drastically reduces the detection, or increase, it makes it faster to detect objects, right? So like a lot of these things, they're kind of shooting for like real-time object detection, meaning you could take like a live video feed at 30 frames per second and be continuously you know, running object detection on that. So I think here they say they're only at 5 frames per second, but there's already much better or you know, faster models than this, like YOLO, and there's, you know, there's these different like YOLO v3, and so those are, you know, those are slightly better, but the point for us right now is to just understand how this works. How can you train a model like this? What do the targets look like? What do the outputs of the model look like? And so that's what we're going to try to do. Okay, so yeah, and then if you're not familiar with these different data sets, like they're really just like different sets of images that have been labeled by humans, and those are what they use as training data for these models, and they also use them as benchmarks to compare the model's performances against each other. So okay, and then yeah, like let's just scroll down here to something like this. So this is what we're after ultimately, right? We want to basically put a box around an object and be able to classify it and say, okay, this is where it is and this is what it is, right? So that kind of combines the two first parts of this series, where one, we just like counted things. We said, okay, yeah, there's 2 circles, 1 line. That was the first video. The second video, we figured out where on the image, you know, we've classified the pixels. What we're, you know, this is going to be much more useful, right? Because a model that can not only detect what's there, but also where it is going to be much more useful in real life. And then in the next series, we'll go over Mask RCNN, which not only gives us a bounding box, but also gives us a mask for that instance, which means, like, you know, it would basically be a mask that would be the outline of this dog as well as part of the output of the model. So let's get into it. Okay, so then I just wanted to say that there is a torchvision object detection fine-tuning model, or I'm sorry, fine-tuning tutorial. I found this useful, and you should definitely read through this if anything when you're trying to like make sense of all this. But what I really found frustrating about this is that they use this like this import, so this train one epoch like utility function, and you can go like read the source for that to make some sense of what's going on. But I just found that this tutorial didn't really give me an intuition for like how this stuff actually works, but it is useful, and I want to tag it for people so that they can take a look at it, and hopefully that is useful alongside this tutorial. Okay, so let's get into it here. So as we've done in the previous ones, I'm going to skip some of the sort of like code heavy beginnings to visualize our data set first and think about what we're trying to build here, and then we'll go up and fill in the blanks. So we're going to skip the imports, the data set, and the data module, and just go straight to data visualization. Okay, sorry, I decided to make the screen bigger a little bit here, make the video a bit bigger. Okay, so let's talk about this. We already basically know how this works from the other videos, so I'm not going to go into the details. You can change the number of shapes per image, you can change the relative probabilities to build imbalanced data sets and see how your model performs with imbalanced data sets and all that. You can also change the grayscale values of the different shapes. Okay, so but what we care about are the targets. That's what's new here, right? So now the targets are these bounding boxes, right? More or less. So we want to, there's some other details that we'll go into, but more or less what we want to do is train a model to put a bounding box and a class label associated with that bounding box around the image, or I'm sorry, around an instance, right? So but when I say instance, I mean like a specific instance of that class, right? Like a line, we want to be able to put a box around that, or a donut and such, right? So that is what the targets look like. Let's go up and see how we actually build this out. So remember, as before, all of these base classes are all the same. These are just used to draw into these images, right? So nothing here is changing, and I'm going to just skip all that. What matters here is the object detection data set. So this is where the new stuff is. Okay, so self-contained PyTorch dataset for testing object detection and instance segmentation models. So that's a new word. So instance segmentation is, like I was talking about when we were looking at the paper, that's when you also provide the mask of that instance as well. So that's the next video, but I didn't want to make two different data sets that basically do the exact same thing. So that's just a flag. You can basically put a flag in here called target masks. If it's true, then the targets will include the masks, and if it's false, they will not include the masks. You know, which I put a flag there because the masks are not very lightweight, right? They're pretty big if you get big images, so it's nice to not have them if you don't need them. Okay, so note that the specifics of the target formatting is adherent to the requirements of the torchvision Mask RCNN and faster RCNN implementations. That said, this data set should work with any object detection or instance segmentation model that requires the same formatting, right? So like you could also use this on YOLO or whatever other model, you know, maybe the Detectron like models. So yes, so okay, and then you can check out the docs here that I linked to if you want to look at the exact formatting of the targets that we're going for. Okay, so let's look at the build images and targets method. That's what is actually interesting. Okay, so the images are just the images. They're just the same as they've always been. The targets are a list of dictionaries of length, data set size, right? So each image has a dictionary associated with it. In that dictionary, there is what? There are boxes, right? So n is the number of instances / shapes in a given image, right? So the shape of the boxes tensor is n by 4, right? Because you need 4 coordinates to define the box, and you have n boxes, okay? Yeah, and these are just some things, you know, like these coordinates have to be relative to the height and width in number of pixels, right? So if you had a 10 by 10 image, those coordinates all have to be between, you know, 1 and 10, right? Okay, and then the labels, that is the prediction, right? Like what class is associated with that bounding box. So that's just n, because there's just n predictions, class predictions. Then we have masks. We'll go into that in the next video because we're not talking about that for this video. Okay, so let's see. For visualizing data, there was one more utility function that I wanted to go through, which is just how do you display these boxes on the images, right? You can use this utility function in your own projects. And yeah, so let's see. So basically, I'm actually just using a function that PyTorch provides. I think, let's see, is it I believe it's, yeah, like a torchvision utility function. But all it's doing is just taking a list of images and returning the images with bounding boxes on them. And this little part here is a little confusing, so I'll go through that. So the the color that we want to associate with the given box, we want that to match the target color that we've specified in the class map, right? So like if I identify a rectangle, I want to put the bounding box of that rectangle and make it red, so that it's easy to see visually, like, okay, yes, it's correctly identifying that object. And here you can do that with just like a little list comprehension. So class map j.item, so of target color for j in target prediction labels, right? So what is that saying? That's saying it's giving it a list of colors, right? And it's saying take the target color of class j for j in prediction labels, right? So if the first one was a 2, it's gonna, like the first label was a 2, it's gonna go and grab target color for class 2, right? And then it builds that list up and tacks those onto the images, those bounding boxes onto the images. Okay. Hopefully that is useful to people who want to just like quickly visualize their data sets. All right, so now let's go and scroll down and, okay, and then this other thing we haven't talked about is applying a score cut, but I'm going to actually pause on this because we don't even know what the scores are yet, but we're going to look at that in a second when we look at the model. So let's wait a second. Okay, so now we want to load this faster RCNN model from PyTorch, right? So if you like, torchvision has this model zoo, you can check it out, check out the docs, but you basically can access these models with something like torchvision.models.detection.the model, right? So for us, we're looking at faster RCNN with the ResNet 50. Okay, and then we are basically reconfiguring the box predictor, like the very end of this model where it's actually, predicting the boxes. We want to not be predicting the number of classes that it trained on initially, which was like the COCO dataset, which has, I don't know, 100 classes or something. We want to be able to specify the number of classes in our data set so that we can train from scratch. Or even if we're going to use the pre-trained weights, which we should, because I think there are papers that show that fine-tuning is gonna be beneficial regardless of how different the application. Well, maybe not totally regardless, but that's my impression. So even though these look totally different than the COCO data set, which are like pictures of humans, buses, cars, it's still probably going to be useful to start with their pre-trained weights. So we can test it out with both. And then if you put number of classes equals to -1, it will just return the model as is with pre-trained weights or not, meaning like it won't change the box predictor at all. Okay, so let us look at what this model actually outputs, right? So I've got a little test image here, batch size 2, image size 16 by 16, and I want to look at what is output, right? So you got to remember the model.eval here, and then I'm just feeding X this batch of images to the model. Okay, so let's scroll up and see what, oh no, see what it outputs here. Okay, so the input shape, we know that. And then, so what I'm printing here is for key val in output 0 dot items, right? So remember, the model, it takes as an input when it's training and outputs when it's in eval mode a list of dictionaries, right? And the keys of that list are slightly different if it's training or in evaluation mode. And we'll go into the differences, but yeah, so I'm just iterating through that dictionary and printing out what we get. So first, boxes. It's giving us this huge list, like it's predicting like so many things because it has no idea what that image is, right? It has never been trained on these shapes before, so it has, it's just giving us kind of garbage here. But that's fine. It's just a list of, that's our n by 4 shaped tensor there, right? And it's labeling everything class 1, okay? Also not really useful, but we're just getting a sense for what this is built of. And then the scores. So the scores we haven't talked about, but the scores basically tell you how confident the model is about a given prediction, right? Okay, so that's why we need to go back up for a second and look at the thresholding here. So apply score cut. So imagine you have your predictions, but after we train it, we're gonna have our predictions, but we don't wanna just display everything. Even if it's like has a score of 0.1, we don't wanna display that. We wanna put a cut there, and we wanna be able to change what that cut is to on the score, right? So we can do that with something like this, right? It's pretty simple, but what I'm doing here is I'm saying key of value where the scores are greater than the threshold for key value in prediction items. So I'm basically just making a new dictionary, prediction dictionary, where I only have bounding boxes and labels for things that have scores over a certain threshold, right? So that's very important. Okay, so now let's overfit a small batch. We're jumping around a little bit here, but that's okay. So, okay, I was getting some lag there. Hopefully that is gone. Okay, so we're here at the overfit function. It's very similar to the previous videos. So the key here, or one of the keys, is you're gonna have to be a little careful with putting all the tensors that are in the targets on your device. And again, that's something that pytorch-lightning should be able to handle for us, but in this overfit, you have to do that for yourself, right? Okay, so the other thing to note is that the loss is different for this model, right? Or like when you call the model in train mode, it doesn't return predictions like bounding boxes. It returns a lost dictionary, and you use that to do your backward step and or do your dot backward and then take your optimization step on your parameters. Okay, so I'm skipping a little bit here. I ran the overfit. You should run that. You should have it right there in front of you. And then I'm getting my predictions, and I'm applying this score cut of 0.5 to visualize my overfit. And I'm just looking at these very simple images. And the overfit is looking good. So that was all we wanted to check. And feel free to pause at any moment and like mess around with things. There's only so much me talking at you is gonna do here. But the overfit looks good. Now we're gonna go down and look at the lightning module and start training on some more interesting data here. Okay, so the lightning module is pretty much the same as before, but now we've got a new metric. We're tracking the mean average precision of these bounding box predictions. Aladdin Person has a great video on MAP, but yeah, you should check that out. Okay, so then, you know, these are all the same parts of this lightning module. We got our forward step, training step, validation step. We configured our optimizers. We grabbed the model, and we have a little utility function to normalize our images. Okay, so then we can, yeah, I'm gonna pause here for a moment. Okay, so I highly recommend that you go through all these cells on your own. I have already trained on this. It only took a few minutes. I did 3 epochs with 1,000 images with 2 shapes per image, and just the first 2 classes. So that was relatively simple, and it did pretty well. Let's actually look at how it performed. And okay, here we can see that there's 41 million parameters in this model, so they are a lot of parameters. This is a big boy. Okay, so then this version 3, this is what I ran most recently. We can see that the loss is coming down, and the MAP got up to 0.78. I only did 3 epochs, and I only tracked this during the validation step, so there's only 3 points there, but that's okay. All right, then we are gonna, so here I'm putting in version 3 epoch 2. It's 0 index though, so we're gonna load up those, and remember how that works from last time, right? We use these checkpoints that saves our weights and biases every epoch, so we can load those up and then look at how our model performs on some test data. Why is it not liking this? I don't know. Okay, I don't actually know. It just complained for a moment there, but that worked the next time I ran it. And then let's make some predictions. So this takes a second here because it's got to go through this big model. Hopefully not too long. Right, there we go. That didn't take too long. Now we've got our boxes and our labels and our scores, right? And we can visualize these predictions. All right, let's see. Hopefully it does okay. So that looks great, right? This looks really nice. So it's doing pretty well. Let's look at the score threshold though. This is interesting because there might be some things that are getting cut by the score threshold. So if I make this really low, yeah, it's kind of doing a double prediction here, but it looks like the score of one of those is very low relative to the other. And we can actually see that up here. Like this is the one, I think, because there's 3 predicted. 2 of them it's 99% sure. One of them it's 20% sure and 10%. So okay, so that's working well. I encourage you to try that with like all 3 classes. More data, less data, imbalanced data set, more epochs. Just mess around and try to gain some intuition here. Okay, so that is it. Let's wrap up here. So we learned how to use the torchvision implementation of faster RCNN. We learned how the targets and predictions for faster RCNN work. We trained faster RCNN on a simple toy data set with just some simple shapes. and we learned about torchmetrics and how it integrates with torch-lightning a little bit, right? We use that MAP metric, which we hadn't used yet. Okay, so yeah, I just have some suggestions for like how I would, you know, deepen your understanding of this stuff with just like a little sandbox. And so just like in the other tutorials, I have all this built into the PyTorch tutorials pip package. And so go ahead and pip install those. You can just copy these cells either into a Colab notebook or into, you know, into a project of your own locally. And so, yeah, so that's the GitHub page for this project. And okay, so here I made just like a very complicated set of targets, but you know, you could obviously change those and read the documentation for the project for what methods are available and what classes are available in the package. And then you can also use the CV models get faster RCNN method to grab that model and put the number of classes as inputs that you want for your project, right? And this output's not going to really make sense because we just put in a random image. So yeah, I hope that's useful to you. And then I just want to point out here, if I go back to the README of the project, if you go to the, where is it? Oh, right here. So if you go to the Intro to Computer Vision documentation, this is going to take you to another README, and this is kind of a foreshadowing of the next video where we're actually going to, well, I guess 2 videos from now, where we're going to actually apply Mask RCNN to some cool images. But here, this basically has all of the classes that are in the package and documentation on them. Like, so today we learned about the object detection data module, and you can read about that here. Yeah. And then, you know, you can click on anything, and if you want to actually look at the, you know, at the source code, you just click those links and you can get to the source code, which also has doc strings. Okay, so that is it. I hope that was useful to people, and yeah, please let me know how, yeah, if this was useful to you. All right, I appreciate it.